Hello everyone, let us start lecture 11 and topic will continue explanation of corrosion event on the basis of mixed potential theory. In the last lecture we thought that we would be able to complete two situations. One was effect of when a electrochemical process, that means corrosion of zinc is taking place in HCl, rather impure HCl with dissolved oxygen. So, that case we can have 3 cathodic reaction and 1 anodic reaction, and we could see different situations, different effects on the basis of mixed potential theory. So, here we will consider effect of exchange current density on the corrosion rate of an active metal. Now, we know that this exchange current density is the measure of equilibrium, since I c equal to I a for a single half cell. For example, H 2 or rather H plus 2 E equal to H 2. So, this is for a single half cell process. So, this is my I c and this is my I a, opposite reaction, and then we have E, equilibrium of hydrogen, which is nothing but 0.059 pH, and here we consider 25 degree Celsius, 1 atmosphere pressure for hydrogen gas. So, this is when hydrogen gas is at 1 atmosphere pressure. Now, this I 0, if we consider for hydrogen evolution reaction on different metals, let us say we consider zinc and we consider platinum. Generally, here the value is around 10 to the power minus 11 to 10 to the power minus 10 ampere per centimeter square, and here it is 10 to the power minus 4 to 10 to the power minus 3 ampere per centimeter square. So, these values or maybe it might go to minus 5 level. So, the next class I will show some tables, and it is also available in internet, you can just look through what are the values of exchange current density of hydrogen evolution on different surfaces, metal surfaces in acid medium. So, similarly, other cathodic reactions or anodic reactions or any half cell reactions, I 0 can have different values. Now, for example, if I consider a situation like a metal, some metal, it has some exchange current density. See, if the situation is like this, let us say this is I 0 of metal over metal surface, and here m n plus plus n e, and this reaction is considered, and this is my E equilibrium of that metal. And similarly, if I consider E equilibrium of hydrogen, if I consider hydrogen evolution reaction on that metal surface, so I will have I 0 hydrogen over metal surface, and that time we are considering hydrogen evolution reaction, or the Hufsel reaction is 2H plus plus 2E equal to H2, and the corrosion rate is here. So, this is I core equal to I A equal to I C hydrogen over metal. Now, there could be in a different acid, this is in one acid, in a different acid, or the if we change the surface nature of that metal, we can have a situation like this. Here the exchange current density can go to this, and the exchange current density of hydrogen can remain here, or it can change here. Let us say if it changes here, and if we maintain the Taffel's law for both the reactions same, then it will go like this. So, this becomes my I core equal to I A of that metal equal to I say hydrogen over that metal. Now, it may happen that the influence of that metal surface on the hydrogen evolution reaction could be such that this one comes here, but this one stays here. So, that time I will extend this line. So, my corrosion rate will be here, I core equal to I A equal to I say hydrogen over metal surface. Now, these all three are three independent effects. So, here all the time this equilibrium potential remains fixed, and here also equilibrium potential of the metal remains fixed, because we are considering the same amount of metal ion as well as same amount of or the same pH value. So, here it can only remain like this provided H2 is maintained at 1 atmosphere, temperature is 25 degrees Celsius, and everywhere the pH is same, all the acids, then this E equilibrium value will not change, because this equation says that this value cannot change. And here also if the metal ion concentration remains fixed, so this particular E equilibrium of that metal will not change, because here E equilibrium metal equal to E 0 plus m plus n f by 2 n R T by n f ln m plus n. So, this is the concentration of metal ion, because m is nothing but the pure metal. So, that time if this remains same for all the cases, this will also remain same. But since we are changing the exchange current density, so here we have changed, here we have changed, the same hydrogen evolution reaction is taking place on the metal surface of different texture or nature, but the same metal, we can change the texture of that particular metal surface. That means, I am talking about the physical texture. So, or the for example, if a metal surface is like this we can have a small perturbation on the metal surface like this. So, we can have a different I 0. So, like that way we can have change in the corrosion rate. So, you could see that if the exchange current density of a hydrogen evolution reaction increases like this, so the corrosion rate also increases like this, and remember this is in log I scale. So, it is an order of magnitude increase of the corrosion rate. Now, this is on the same metal, but many a times we can have a situation, for example, we can have a couple between this particular galvanic coupling where both have same area. So, this is extremely important. We will see later on that if the area of this galvanic area of the individual component of that galvanic couple are different, the corrosion rate of the zinc of the active component will change. We will see that if the area of the platinum, this area let us say A platinum and this area is A zinc, in case this is greater than this, that case corrosion rate of zinc decreases. If A platinum, or if it is this, corrosion rate of zinc increases. So, we will see that effect. So, that is what we are initially considering, a situation where both have same area. So, that means cathodic as well as anodic reactions are finding anodic reaction that is taking place on zinc. So, area effect we are not considering here. So, now if they are dipped in acid, okay, and if we assume that I0 hydrogen evolution reaction on zinc surface is 10 to the power minus 11 ampere per centimeter square, and I0 of hydrogen evolution reaction on platinum is equal to 10 to the power minus 5 ampere per centimeter square. So, these are some arbitrary values I am considering. These are though arbitrarily taken, but at least we know that the hydrogen evolution reaction on zinc surface in an acid is much lower than the hydrogen evolution reaction exchange current density of hydrogen evolution reaction on zinc surface is much lower than the exchange current density of hydrogen evolution reaction on platinum. So, we are maintaining that difference by assuming these two values. Now, what would happen? And if we assume that beta is always 0.1 volt per decade of current density, of course, beta C would be negative 0.1 volt per decade and beta A would be 0.1 volt per decade, and these values are all the time they are similar in all the reactions that are possible, and this acid is pure as well as no dissolved oxygen. So, that case only one cathodic reaction, which is H plus 2E equal to H2. This is possible. Now, we have to see the effect of that galvanic coupling as well as the effect of that exchange current density. Now, let us draw E versus log I. Okay. We will have zinc equilibrium and I0 zinc over zinc surface. I assume it to be 10 to the power, let us assume it to be 10 to the power minus 9. ampere per centimeter square. And if we consider pH to be 1, if we consider pH equal to 1, so E equilibrium hydrogen equal to minus 0.059, pH equal to minus 0.059 volt. So, this is minus 0.059 equilibrium hydrogen. Now, the hydrogen evolution reaction on the, let me shift this particular axis a bit. Okay. So, this point will lie left to this point. So, this is I0 hydrogen over zinc equal to 10 to the power minus 11 ampere per centimeter square. And on the platinum surface also it will have this hydrogen evolution reaction will take place. So, potential will not change because pH is maintained same for both. The pH of the solution is always 1. So, now it is hydrogen evolution reaction on platinum surface. So, this point, or I can draw further right, we have to maintain that log scale ratios. So, this is I0 hydrogen over platinum equal to 10 to the power minus 5 ampere centimeter square. Now, it will go like this. Now, so I will just change the slope little bit. So, this is for a situation where there is only one zinc is dissolved or zinc is dipped in the acid, but when is this couple is dipped in the acid. So, hydrogen evolution reaction also takes place on platinum surface. Now, these two reactions, this one and this one, both have beta to be 10 to the 0.1 volt per decade, that means the cathodic Tafel slope, and they are parallel. And since there are these two cathodic reactions are taking, so same cathodic reactions are taking place over zinc as well as platinum surface, and as per the mixed potential theory we have to add them and then take a log. So, we will find that this new line, which is the addition line, let me draw it with the green color. So, that will be, we just add it up and then the parallel line will go like this. So, the green line is IC total equal to IC hydrogen evolution over zinc plus IC hydrogen over platinum equal to IA zinc, sorry, this line is this, and this particular line belongs to IA zinc. Now, I could see that as per the mixed potential, this point is the E mix. Now, and here we maintain IC hydrogen equal to IA zinc equal to IC hydrogen over zinc surface plus IC hydrogen over platinum surface. Now, we could see that if platinum is not there, only zinc is present. So, that case this will be my I core equal to IA zinc equal to Ic hydrogen over zinc surface. Of course, this is the mod, because that negative sign is nothing but the current, this Ic is flowing opposite to Ia, and this would have been my E core, and the condition is when platinum is not present, and this is the condition when platinum is not present. Now, we could see that since the exchange current density of hydrogen evolution on platinum surface is much higher than the hydrogen evolution exchange current density on zinc surface, I could see that the corrosion rate has gone up from this value to, which is Ia zinc equal to I core zinc for couple situation, for the galvanic couple situation. So, it is very clear that if we connect any structural component to a noble component, and the exchange current density over the noble component of that cathodic reaction that is taking place in that particular equilibrium, in that particular electrochemical system, I will have much higher corrosion rate of that active component. So, this particular diagram explains the corrosion event taking place when exchange current density over the noble component in a galvanic couple is much higher. Exchange current density of the cathodic reaction, of course. So, let us solve this particular problem with the following data. So, these are the data that are available. So, whether we can get the value of, so our solution would be what we need: E mix, we need to find out E core when platinum not present, when platinum present. Now, if and the value I core is given, zinc when platinum is not present is equal to 10 to the power minus 7 ampere per centimeter square. This is arbitrarily chosen value. Now, can we get, this is the value given. So, these two we have to calculate. Another thing we have to calculate is I core zinc when platinum is present. This is we have to find out, and individually we have to find out Ic hydrogen over zinc surface as well as Ic hydrogen over platinum surface. We have to find out at E mix when platinum is present. So, we have to solve this. So, in order to solve this, we have to go step by step. First, let us find out E core. So, in this case, we know that E equilibrium hydrogen equal to 0.059 volt, since it is pH 1, beta C equal to minus 0.1 volt per decade. So, neta C, which is the cathodic over voltage, equal to beta C log IC by I0. So, here neta C is nothing but E core minus equilibrium hydrogen equal to 0.1 log IC hydrogen over zinc surface divided by I0 hydrogen over zinc surface. Now, we know all those values except this. So, let us put them. E core plus 0.059 equal to 0.1 log 10 to the power minus 7 divided by 10 to the power minus 11, since at this point IC hydrogen evolution over zinc surface is equal to I core. So, if the over voltage is this much, so this over voltage is calculated here. So, equal to this becomes 0.4. So, E core equal to minus, so there will be minus sign, 459 volt. Now, we can calculate, in order to calculate E mix, this is stage 1, 2, we have to calculate E mix. For that, we need to calculate first E equilibrium zinc. Let us calculate this. This is also easy because we have to consider over voltage this neta A. So, this over voltage is beta A log of IA I0 zinc over zinc surface. So, then it becomes E core minus E equilibrium zinc equal to 0.1 log 10 to the power minus 7 divided by 10 to the power minus 9 equal to minus 0.2. So, then equilibrium zinc equal to E core minus 0.2 minus okay. So, this should be like this. Sorry, this should be plus. So, this becomes 0.459 plus 0.2 equal to 0.659 volt. Now, interestingly, we have to find out this point, that means E mix we have to find out. So, if we see E mix let us say some value. So, E mix minus E equilibrium hydrogen, let us say E equilibrium hydrogen equal to, I can write this equation equal to neta C prime equal to beta C log IC hydrogen over I0 hydrogen. Now, if I say this, I am now considering over voltage in the blue color, it is green color, I am considering this over voltage. Now, can I find out this point? So, here this is the condition neta C, and since this is a parallel, this green line is a parallel line for this. So, that means slope for the green line is same as the slope for the black line, that the cathodic polarization line for hydrogen evolution. So, I can find out this particular point, which is let us say T point. If I try to find out the T point, so the T at T, I see that I C hydrogen, or IC total, if I put I0 total for hydrogen reaction equal to I0 hydrogen over zinc plus I0 hydrogen over platinum. So, equal to 10 to the power minus 11 plus 10 to the power minus 5, which we can consider as 10 to the minus 5 ampere centimeter square. So, once we know this, I can put it up here. So, this neta C prime equal to E core plus 0.059 equal to minus 0.1 log 10 to the power minus 5, So, some IC hydrogen total divided by I0 hydrogen total over zinc as well as platinum surface. So, I am just adding plus sign here just to indicate that this is the total value of exchange current density. So, this point I am talking about. So, the T point is nothing but IC hydrogen, or the way we are notifying I0 hydrogen, T means total. So, this let us stop here. So, you try to solve this problem. Once you know this, then you have to consider another equation which is nothing but this over voltage, which is A prime, and try to solve these two equations we are generating and try to see whether you get E mix. However, we will continue this problem and solve completely in our next lecture. Let us stop here. Thank you very much.